My name is Stefan Rombouts. I got my training as a computational physicist at the University of Ghent in Belgium. I've been working as a researcher on quantum many-body problems for quite some years, but then I moved on to industry, to things that had nothing to do with quantum physics. But somehow I felt the desire to get back into stuff more related to quantum physics and more closer to the front lines of science and engineering, and I got this opportunity to start the beginning of this year in Parity Quantum Computing in Germany, in Ulm. I started, and so I was very glad to take that opportunity to get back to quantum physics in a certain way. So we are really pushing the frontiers of computation in this project. The frontiers, the physical frontiers. So it's really physics, the laws of nature that place the limits here. Traditional computers are getting very close to these limits. Transistors are getting smaller and smaller each time, and they start to be very sensitive to quantum effects, and it's causing problems to miniaturize even further. So quantum computing takes a completely different approach to that, trying to take advantage of these quantum effects and to see how we can still do quantum computations at that level, which in principle could promise even more powerful computations or even more efficient computations in energy resources required. Of course, this is a long-term goal. At the beginning, we have to figure out how to do it first. So that's the real challenge that this project is trying to overcome. And the idea is that later, when we overcome some of these hurdles, we can also put these devices to use for practical uses, to really perform powerful computations. Now, nowadays, for these high-performance computations, people use big clusters where you have hundreds or thousands of PCs put together in racks to try to model very complicated systems so that you can do these calculations and predict, for example, the weather or how materials will behave under stress, and a lot of difficult engineering problems really are solved that way today. What we see now in QSolid is that one of the first important applications of quantum computers, when they become practically available, will be to take part in these high-performance computing projects as accelerators for certain specific tasks. So you might have a very general task to calculate properties of new materials that might depend for certain parameters on aspects of quantum physics. Then it would make a lot of sense to do the quantum mechanical part of the calculation on a quantum device, because it has all these quantum correlations built in its structure and its electronics. And you don't have to run expensive simulations only to model these quantum effects. So there will be a very interesting interplay on the one hand between large-scale modeling of new materials, for example, and these quantum calculations that can help to speed up the simulations. Another interesting application will be optimization problems. There's a lot of things that have to be fine-tuned, for example, in a production process, what part you produce first, in what order do you organize the layout. And there also people today use very large simulations in order to optimize production processes. For example, we at Parity QC, we have found a way to map certain combinatorial optimization problems onto quantum problems so that we could harness there also the power of quantum computing to speed up these optimization problems. And to make this happen, it's important that classical simulations on these high-performance computing clusters can be connected smoothly to the quantum devices when they become available. That you can, say, call a subroutine from one part to the other, get back the result very quickly and work on that with the other part. And this is the whole challenge that we are tackling in Work Package 10. How to make high performance clusters using traditional computers interact swiftly with new quantum hardware. You could ask, why are we doing this right now if we don't have quantum hardware? Well, it's important to be ahead, because as soon as quantum hardware does become available, and we hope to have some real devices at the end of this project, then we don't want to wait another 2 years in order to tune the software to make a good use of it. We want the software to be ready when the hardware, the quantum hardware, is ready, and that's what this work package focuses on. We really have to design how we couple HPC computers with quantum computers, and we can do this in several different ways. One way might be more suited for one type of application, another way for another type of application. It basically depends on how often these two parts have to talk to each other and which part will be doing most of the work. And so for us, it's a real challenge right now to try to imagine how such a machine would be used in 5 years' time, because there isn't yet such a machine. So it's a real challenge for us to imagine how will people use these things, what would be the best way to use these things, and then to design the interfaces between the components in an optimal way for those use cases. So that's, I think, the most fundamental challenge that we face right now in the work package.